With a basic understanding of the shell world, the terminal, some of the programs that we have there, the way that we can link these programs together through input-output redirection, we can now approach the topic of shell scripting. The motto here is that everything's scriptable. We do not want to type out or copy and paste a long series of commands very often. We want to solve a problem once, and then ideally we do want to bundle sets of commands or just a single command in an executable script for repeated use. These scripts don't have to be complicated. I have a very simple example that I've used many times down here that cumulatively saved me a lot of time. What these scripts need to do is reliably do something that is useful in a way that is done quicker by saving it into a script than typing it out manually. There's no limit to the number of scripts that you can write, but you've kind of got to remember the names, or at least know where you put things and name them in a way that you can easily recognize what the function is. So the directory where all of this lives should be in your path. Here's a simple script that is called ees.readout, which I have used to connect to a server. That server doesn't exist anymore, so that's a good example to include here. Usually on the shell, I just typed ees.r and then tab and enter. The tab would complete readout because there was only one server that started with R that was in the EES domain. And then I just hit enter, and what it would execute is SSH minus 2y username at this machine. Instead of having to type all of this out, I simply could execute this. It even allowed me to forget what the server was named, because all I needed to remember was the R. Or I could find the servers very quickly by looking in the directory that would save these scripts, because there were several different machines, some of which I didn't connect to for a while. So this was a good external memory piece. Very simple. First line here, characteristic of a shell script, is the interpreter. You use the octothorpe exclamation point and then the path here /bin/tcsh. So I want this to be executed in a TC shell. So any series of commands that you can type at the prompt manually can be bundles in a script. And what I often do is I develop code on the prompt to kind of test out certain things, and then develop my script in parallel in some editor to ensure that all of that work that I just put into finding the right sequence of commands is saved, and I don't have to remember that in the future. I mentioned that the shell provides you with variables. There's the predefined path. You can use your own variables. You can use set or set env or export, or just give it a name equals something, depending on whether you use bash or tc shell. And then flow control on top of that allows you to write actual programs. So you can test conditions, you can run loops. So as a reminder, variables here, regular variables that are visible just in the current shell. Remember that spaces here are important. So for the tc shell, we would say set txt space equals space quotes hello world exclamation point. In the bash, we would just say text equals hello world, and then to access the variables, it's the same for both tcsh and bash. We would just say echo $text, the variable name. So the $sign indicates to the shell that the string that follows right after without a space is a variable name that it should look for. One thing that is extremely useful is backticks. This executes a command in a subshell. It runs the bash with the command given and takes the output and hands it back to the script that's currently executing it. So here, quite often, you'll do something where you need a list of files or something else, or you want to grep for something, find a list of lines in a file. Here, we're using the bash syntax to assign the variable, right? Remember this, but this works in tcsh just the same way. So we're listing all of the files that end in .py in the current directory, and then that list of files is stuffed into the variable that we call files. If you want the output of some program saved to a variable, that is the recipe to do that. Okay, if you want to assign an environment variable that is visible at the current shell and scripts called from this shell, so a global variable that, subprograms like ls or others could see, you would use in tcsh the setenv command that we've already seen, and you could use any name. I just use path here because we have seen path before, but you could call this foo or my files or some other variable name that you can come up with, and this will then be visible to any script or program that you call from within the current script. Next, quotes. There are two types of quotes: single quotes and double quotes. Single quotes force the literal interpretation of what's in the quotes. So if we set text to hello, output we set to I want to say $text, and then we echo the output. And remember, these are my shortcuts for the prompt. If we echo $output, what the shell does is it looks what is in the variable output, single quote, I want to say text, $text. And so that is what's being printed. The difference to double quotes is they group words, but the variables are still recognized and interpreted. So when I make output here and I say, I want to say $text, the shell is going to look what is in $text, and it finds hello. So it sticks hello exclamation point in here. And then if we say echo $output, we find the return text to be I want to say hello, right? Difference here is $text was not dereferenced. It was the literal interpretation of $text. And here $text was replaced with the value that is in that variable. There's a vast range of conditions that one can test for. Here, I'm just giving a taste of what's possible in Bash, and I'm not going over every single one of these. Note that the double bracket is an important command in Bash, which returns either 0 or 1 based on the evaluation of the condition. It is important that you use that around the conditions that you want to test. So here we could give it a string and check whether or not it's empty or not empty, whether two strings are the same or not the same. If you want to compare numbers, you would use these comparisons. And for logic, you can use the exclamation point for not some expression. You can say X and Y using the double and or the double ampersand. And you can say or by using the double vertical bar. You can also test for various file conditions, whether a file exists as -e, whether it's readable, whether it's a directory, writable, etc. Now that we know about conditions and how we can set them up, we might want to wrap this into flow control. So here is an example of if some condition, so -z is the string empty. So if the string is empty, then echo the string is empty, or elif -n, can go back looking, -n, not empty string. So if the string is not empty, then you should say the string is not empty. And then you should say else, well, this probably never happens. You will have to come back and look at the syntax for this repeatedly until you've done it enough that it becomes very fluent. But for the if statement, we have if as a keyword, the condition that we want to test, semicolon, then, and then the body of the if condition. And then you can say either else, whatever is the else branch, you will have to end it with phi in the bash shell. You can also test for other conditions many times. In this if-else branch here in the bash, you would use elif, your new condition, semicolon, then, etc. You can test for logical combinations. So you want the condition x and y to be true, then this happens. You want to test for equality, some regular expressions, larger, smaller than, or whether a file exists. This is what these examples look like. Let's go over loops. Here are some basics. That's with a focus on the bash shell again. The syntax is for some variable in a list, semicolon, do something with that variable at each iteration step. And at the end, you use the keyword done. You can usefully just use a string with a wildcard here, which is interpreted as you want to build a list of files. So here, that example looks in the directory /etc/rc dot asterisk. So all the files that start with rc dot in the directory etc are in that case going to be just printed to the screen. Maybe you want to look at them. Key thing is here, you do not have to use backticks and ls for this. This is a built-in feature of the shell. You may want to test for ranges. You can say for I in the range 1.5. So this will go from 1 through 5. Do this, done. And perhaps even a step size, go from 5 to 50 in step sizes of 5, which is extremely useful to do sometimes. You may want to do a while loop, while true, do something. We've seen that construct before. Perhaps you want to read the lines in a file, so you can say cat file, pipe it into a while loop, while read line, do something. This is going to require a lot of practice, but all the tools that you need to do quite complex tasks automatically in the shell are there. You have loops, you have conditions, flow control to string things together. You can write your own programs. A script itself can be considered a function, right? So it's all there. The last thing that we need is reading command line arguments, right? If you consider a shell script a function, you need to give it some input. Now, shell scripts can take input from the command line. If you do not want to deal with how to set up the minus flags and give that arguments, the most basic way to do it is with positional arguments. The shell uses special variables $1, $2, /$n to get the first, second, etc. argument. You can use the special variable $octothorpe here for the bash, or argv to get the total number of existing arguments if, for instance, you want to just loop over all the arguments that have been given. So simple example here, using the bash shell, we want to echo the argument 1 with $1, argument 2, $2, argument 9, $9. So if we call this script arguments.sh and we give it A, B, C, D, E, and so forth arguments, we now get that output from the script here. Argument 1 is A, argument 2 is B, ... argument 9 is I, and we're not dealing with J, we just ignore that. And this completes everything that we need to write complex programs in the shell environment that allow us to look for data, to process data automatically, to call other scripts that take our processed output, turn it into plots, to do a whole host of very complex work. And it allows us to use a large range of existing tools that we'll talk about in the next session, the existing Unix power tools that are so efficiently built to work on text files and to sort and isolate certain patterns that we might be interested in, to do basic math on some of the data that we might give it. Together with the scripting and the power tools, this becomes an extremely useful environment to be doing our data analysis in.